So, we have been learning about the magnetic field and how it is calculated. I introduced Biot-Savart law, which said that magnetic field due to a loop at point r is given as mu 0 over 4 pi integration I d l prime cross r minus r prime over r minus r prime cubed, and then we change this to mu naught over 4 pi integration d v prime j r prime cross r minus r prime over r minus r prime cubed. We also learned about vector potential. A such that magnetic field B is given as curl of A r, where A r is nothing but mu 0 over 4 pi integration j r prime over r minus r prime d v prime. I had also indicated that calculation of magnetic field is necessarily more difficult than that of electric field, because it involves a cross product, and sometimes imagining in 3 dimensions is also more difficult when it comes to magnetic field. Therefore, what I am going to do is solve many problems that involve calculation of magnetic field. To start with, I am going to solve one problem from Zangwill's book, and this is problem number 10.8. There are 3 parts to it. Part A says, let I be the current carried by a wire, and I will put it as thin wire from my side, bent into a planar loop. So, the problem says that here is a wire that has been bent into a planar loop, and that has been bent into a planar loop, and it is carrying current I. Then I want to calculate at an observation point P the magnetic field, and we want to show that the magnitude of magnetic field at P is B. We are talking only about magnitude. So, I am going to write no vector here, is equal to mu 0 I over 4 pi integration d phi over r phi, where phi is the angle, polar angle, and r phi is the distance from observation point P. So, let me explain the problem. What it is saying is that here is a loop carrying current I, and I want to calculate the field at this point P. In that case, this field is given by the expression that we have shown. So, P is given as mu naught I over 4 pi 0 to 2 pi, I had forgotten to write it earlier, d phi over r phi, where these are given as, suppose I take this dashed red line as the x axis. Here is the distance r phi and here is the angle phi. So, in a way I have taken P as the origin. So, let us solve this problem. Here is the loop. Here is point P. Let the origin be here, and I am taking line joining O and P as the x axis. That I can do without any loss of generality. Even if I do not, it does not really matter, because I am going to solve the problem in the most general way. So, B at P is given as mu 0 I over 4 pi integration d l prime cross s minus s 0 over s minus s 0 cubed. Let me explain what this is. The vector from O to S, O to P is S 0, and vector from O to P is S, vector from O to P is S, because this is where I am calculating the field, and the vector from the d l that I am taking, d l prime that I am taking, is S naught, and I am integrating over this naught. So, maybe it will be better if I call this not S naught, but S prime. So, you see, once I write this as S and S prime, then it does not really matter whether I am taking P along the x axis or at some other point. So, let me write that once more. So, here is this loop. So, in general what I am writing is, this is my origin, here is point P somewhere, and this vector is S, and a line on the loop is S prime, this vector, and there is this d l. And I have to calculate this magnetic field. The magnitude of magnetic field is going to be mu 0 I over 4 pi integration magnitude of d l prime cross S minus S prime divided by S minus S prime cubed, which is nothing but mu 0 I over 4 pi integration, this is over the entire loop, d l prime magnitude perpendicular, I will explain in a minute what this perpendicular is, magnitude of S minus S prime divided by magnitude of S minus S prime cubed. And okay, that is it. Now, d L prime perpendicular is the component of vector d L prime perpendicular to vector s minus s prime, or same thing, vector s prime minus s, because we are talking about magnitude. So, let us see, d L prime perpendicular is going to be d L prime, just the magnitude, sine of theta, where theta is the angle between d L prime vector and s prime minus s vector. Let us see this more clearly. Here is this loop, here is this point P, here is the vector s prime minus s, here is d L. I am just going to focus on this. So, let me have a look at this part. If I look at this part, here is this portion of the loop, here is vector d L prime, should have been prime, here is vector s prime minus s, here is the angle theta. So, d L perpendicular, I am going to show it by blue, is going to be this. d L prime perpendicular. Now, suppose the angle from S to this S prime minus S is phi, then this d L prime is d phi. And what is the expression that I am calculating? I am calculating B P is equal to mu 0 I over 4 pi integration d L prime perpendicular mod s prime minus s divided by mod s prime minus s cubed. Now, you notice that d L prime perpendicular over mod s prime minus s is nothing but d phi, and mod s prime minus s is nothing but r phi. And therefore, I can write B at P as equal to mu 0 I over 4 pi integration d phi mod s prime minus s square divided by mod s prime minus s cubed. This square comes because of this, and d phi goes from 0 to 2 pi, and this immediately gives you that P is mu 0 I over 4 pi integration 0 to 2 pi d phi over r phi. You see, it involved a little bit of playing around and visualizing how the vectors are changing. Let's go to part B of this problem, and part B says calculate using the formula derived in A, the magnetic field at the center of an ellipse of semi-major axis of size 2a and semi-minor axis of size 2b. So, what we want to do is now calculate the field at the center of an ellipse which has semi-major axis 2a and semi-minor axis 2b. Using polar coordinates, this would be phi. In the case of ellipse, r phi is given as AB over square root of a square cosine square phi plus b square sin square phi, and therefore, B at the center will be equal to mu 0 I over 4 pi integration 0 to 2 pi d phi over r phi, which in this case will come out to be mu 0 I over 4 pi integration 0 to 2 pi d phi integration of a square cosine square phi plus b square sin square phi over a b. This integral d phi square root of a square cosine square phi plus b square sin square phi can be brought into the form of a complete elliptical integral of second kind. So, the field for an ellipse at its center will be given by an integral which is the complete elliptical integral of the second kind, and I will leave it for you to complete it. The next problem that I am going to do is from Jackson, problem number 5.2, which says given a solenoid of infinite length, show using the formula, and I want to remind you we had derived this in one of the previous lectures. And it is the solution of problem 5.1 of Jackson. So, formula is B at any point is given as mu 0 I over 4 pi gradient of omega, where omega is the solid angle formed by a closed loop at the observation point. So, it says show using the formula there B equals this, which we had also solved earlier, that B inside a solenoid, and I am going to call it perfect solenoid, so that the surface current is in phi direction and no other component is B equals N I Z. I am using cylindrical coordinates. So, let me write this. This is B. So, x and y components or rho and phi components are 0, and B outside the solenoid is 0. It is an infinitely long solenoid. So, we are going to use this formula here. Okay, so, let us get the solution. So, here is the solenoid, make a long solenoid, and here is the point. Let us say this plane in between somewhere is z equals 0 plane, and here is this current flowing like this. The surface current K, which is given as N I in phi direction, where N is number of turns per unit length, and I is the current in the wire used to make the solenoid. So, I can use either of that. So, let us look at a point here at height z. I want to use the formula B equals mu naught I over 4 pi grad of omega. So, for that we first have to calculate omega at the point P. Let us call this P. Now, it may be tempting, and I want to tell you this wrong way, it may be tempting to calculate omega due to one turn. So, let me show this omega due to one turn. I am showing it in green, and then integrate it to get omega by all turns, and then differentiate, then take its gradient to get B. But this will be wrong. Why will it be wrong? You see, omega by all the coils together is going to be infinity, right? Everything is making something. And what we are interested is, we are interested in the change in grad B, grad omega due to each loop or each turn, which is B due to each turn, and then add all the B's. So, you cannot just add omega and then take differentiate, nothing will change. So, what we are going to do is, we are going to calculate omega due to one turn, and then get B due to it, and then integrate, over all turns to get B. That is the strategy. Recall that omega is positive or negative depending on whether the point P is inside or outside the loop. For this, go back and see the solved problem. In a previous lecture. So, I will just refer to that. So, you see now, if I have this solenoid, here is a plane z equals 0, here is a point at height z, and let us say it is at some distance S naught, where I am using cylindrical coordinates. So, S naught vector, and I have a loop, current loop, which I am making at height z prime and thickness is dz prime. Then the angle or the solid angle that this current loop makes at this point, observation point at P, is going to be equal to ds, the area of this loop, dot the distance. So, r at this loop minus this r naught divided by r minus r naught cubed, and this integrated over the entire area, where ds is this area here of the loop inside. So, here is the loop and I am taking some ds area. Since ds is in z direction and I am using cylindrical coordinates, so I can write this as some magnitude ds in the z direction, and therefore, omega at point P is going to be integration ds, whatever the area is, z minus z 0 divided by r minus r naught cubed, where mod r minus r naught cubed is nothing but S minus S 0, where S and S 0 are the vectors for the area element, and this point square plus Z minus Z 0 square raised to 3 by 2. Slight clarification, I have changed the notation here. So, this height of the point is S 0 and Z 0, and the height of the loop is at Z. Slight correction. And therefore, in the solenoid, where I have taken this point P at S 0 vector and Z 0, and I have taken a loop, current loop at height Z omega P, the solid angle that this loop is making at the point P is nothing but the area d s Z minus Z 0 over at R minus R 0 cubed integral. And therefore, small field due to this loop is going to be equal to grad of d s Z minus Z 0 over R minus R 0 cubed, and let me put this grad with respect to 0th variable, because the gradient is taken with respect to the coordinates of P point. This is B. It is going to have all three components. So, this I can write as equal to I d by dx of ds Z minus Z 0 over R minus R naught cube. Let me write this x 0 plus j, the y component, d by d y 0 integration ds Z minus Z 0 over R minus R naught cubed plus k d by d Z 0 integral of ds Z minus Z 0 over R minus R naught cubed. This is for the upper portion. So, this is for all the loops in the upper portion, any loop in the upper portion, and total B, I should have written mu 0 I over 4 pi. Now, I is nothing but k dz or n I dz, and therefore, B due to the upper portion is going to be equal to mu 0 n I over 4 pi integration dz starting from z 0 to infinity grad of all that omega. Let me just remind you that this corresponds to this. Contribution from the lower portion. From the lower side, the current is going like this. Then you can see that P is outside the loop, and therefore, now B from the lower side is going to be minus mu 0 n I over 4 pi integration minus infinity to z 0 dz grad of omega from the lower side. And then let me write this upper net B, B total is going to be equal to B upper plus b lower. So, now we have all the ingredients that we need to calculate the field. So, let us look at the upper part first. So, B upper is mu 0 n I over 4 pi integration d z z 0 to infinity grad of omega, and we have found the grad of omega to be x component, y component and z component. X component is I d by dx of z minus z 0 over r minus r 0 cubed. This is going to be give some x component. Now, for the lower portion, we get the x component, which is going to be I d by dx of z minus z 0 over r minus r naught cubed, and these are integrated over z. Z 0 to infinity dz minus infinity to z 0 dz, and there is a minus sign for the lower part. Now, I leave the manipulation to you to show that B upper x component is minus B lower x component. It is very easy to show. Just do the substitution. Z minus Z 0 equals y, and then take the derivative, and you will see that the two come out to be opposite to each other, therefore, they cancel. The same is true for the y component. So, we are left only with the z component, and what we have then, B upper z component is equal to mu 0 n I over 4 pi d by d z 0 integration z 0 to infinity dz z minus z 0 over r minus r naught cubed. The way this expression is written, it is wrong. And this is to remind you that I am first calculating the field and then integrating it. Therefore, writing it in this manner is not correct. What the correct expression would be, that I first calculate the field and therefore, B upper I should write as mu 0 n I over 4 pi. I first do the derivative for the z component z minus z 0 over r minus r naught cubed, this is with respect to z 0, and then integrate from z 0 to infinity. this is the correct expression. This relates to my statement earlier that first you got to calculate the field due to each loop and then sum that field. Now, I am going to use a trick. I am going to say that d by d z 0 z minus z 0 over r minus r naught cubed is equal to minus d by dz of z minus z 0 over r minus r naught cubed. There was an area element ds also out here. Let us go back and check. So, here is this ds, I am just showing it to you, that should also be there. You see this. So, B upper is equal to mu naught n I over 4 pi integration z 0 to infinity d z with the minus sign outside partial z of z minus z 0 over r minus r naught cubed d s. Now, you see the trick that I used of changing the variable d by d z 0 to minus d by d z is very handy, because now I can perform this integral straight away, and therefore, it gives me minus mu naught n I over 4 pi integration z 0 to infinity d s over z minus z 0 over r minus r naught cubed d by dz dz, which is equal to minus mu naught n I over 4 pi d s integral over r minus r naught cubed z minus z 0. Which is minus mu 0 n I over 4 pi, this is at z 0 and infinity. So, it is going to be d s cosine of theta over distance square at z 0 and infinity, right, where, let me make a picture. Here is a little d s, here is d s vector, it should be modulus. We are taking the component of d s perpendicular to the distance and square. So, this is a d omega. So, I am integrating over this d omega. So, what is this? This is integration mod d s cosine theta over the distance of that square, integration over the area at z naught and infinity is omega at infinity minus omega at z 0. That means, what I am looking for is at this point P, I am looking what is the solid angle that this far away area makes, and what is the solid angle that this area right here makes. You can see that the area far away makes 0 solid angle, and this makes 2 pi solid angle. and therefore, I can write this expression for B as, so this whole thing therefore becomes minus mu naught n I over 4 pi 0 minus 2 pi, which is nothing but mu naught n I over 2. So, what we have obtained is that if I have this solenoid z equals 0 at a point somewhere in the top, the upper portion gives B at any point, this point, it could be anywhere in this plane, B z is equal to mu naught n I over 2. In exactly the same manner, and then I will leave it for you, the lower portion B lower, this is upper, will give me again mu naught n I over 2. Therefore, B is equal to B z, which is mu naught n I, a well known expression. And this is for points inside the solenoid. We can do exactly the same calculation for points outside. For points outside, again when I take the solenoid, and I take a point outside, you will see that solid angle omega for z equals infinity is 0, and omega for z equals z naught, which is right here, will also be 0. So, B upper is equal to B lower z component is equal to 0. So, there will be no field outside. So, we have shown that field inside is in the z direction and there is no field outside. I will ask you to go back and check my expressions for the x and y components of B inside, and I ask you, did I do it correctly? I said that d by dx and all that is 0, whether that is correct. So, I said x and y components are 0 for each half of the solenoid. Is that a correct statement? Or is the correct statement as follows? The x and y components due to the two halves of the solenoid are in the opposite directions, and therefore, they cancel. check this. Okay. It's this statement will come out to be correct. So, I want you to go back and check it. A related problem and this is Zangwill 10.3 part A is show that the flux passing through a semi infinitely long solenoid, that means one end is at z equals 0, the other end is goes to minus infinity. Show that the flux through the open end is half of that deep inside the solenoid. Now, this should be a very easy problem for you, because I have just calculated B z due to half the solenoid, and this came out to be mu n by 2, and therefore, immediately it follows that the flux is 1/2. To summarize this lecture, solved problems 10.8 of Zangwill and 5.2a of Jackson, other parts will follow, and 10.3a of Zangwill. In 5.2, I have left for you to check a couple of steps, and I expect you to do them. Thank you.